morning, very good morning students. One problem on thermodynamics we will solve today. Then we will go to kinetic theory of gases. Probably one of the little hardest chapter, but most of the things of kinetic theory of gases we have studied in chemistry. That is why we will see the physics side of it, okay, later. Now one problem we will solve on thermodynamics. Later we will move on to the new chapter, kinetic theory of gases. Okay. So I'll write down the question first. I'll write down the question. Okay, here it is. A thermodynamic, please listen and write. A thermodynamic, okay, visible, no problem, no. A thermodynamic system is taken from an original state. It's taken from an original state to an intermediate state by linear process shown in the figure. So here is a diagram. So this is as I told you, is pressure and volume in meter cube, pressure in Newton per meter square they have given. This is how it is given, and this is 2 meter cube volume, this is 5 meter cube volume, this is 300 Newton per meter square pressure, and this is here it is 600. Okay, this is D, E, and this is F. Next, continuation of the question. Its volume is then reduced to the original volume from E to F by an isobaric process, calculate the total work done. Calculate the total work done by the gas from D to E to F. D to E it goes, D to E, E to F it goes. So it covers this much of area. Okay, so remember, area under PV curve is the work done. Area under PV curve is a work done in a thermodynamical process. So area under PV curve is a work done. So what is the area now? What is the area? Area is area of the triangle. Area of triangle DEF is equal to work done. So that is triangle, no, half. Then the height is DF. Breadth is FE. FE is the work done. So half into, what is DF? DF is 600 minus 300. FE is 5 minus 2 is equal to work done. So that is, this is 300 into 3, this is 900, this is 450 joule is the work done. This is how we solve such problems. Okay, so that concludes thermodynamics. We will again discuss it as we discuss it for NEET. Of course, synopsis obviously will be in detail. Okay, so let us move on to kinetic theory of gases. So please take them fast. So let us discuss kinetic theory of gases. Kinetic theory, this is very much studied in chemistry. You have studied kinetic theory of gases. So gases are higher in volume and they are very much random in their nature. A weak van der Waals bond or van der Waals force holds these molecules loosely together, correct? This is what we have studied. Okay. So that is why obviously their volume is larger. So whenever a gas, if it is seen with high pressure, then obviously what happens, it is more compressed like. So the randomness to it is high pressure alli adu volume kadime irtade, compress adag irtade, so it tends to have the stronger interactions between the molecules. And if I heat it, its density becomes less. Okay, its density becomes less, so that they move away. Its volume expansion takes place, so that the molecules move away, so that the interaction also becomes a little weak. Ideally, for any gas, not to have interactions with its neighboring molecules, high temperature should be maintained. This is the first point. Also, in addition to that, if you maintain low pressure, then obviously its volume will be larger, no? So they tend to go away. So if you maintain high temperature and low pressure, the volume increases and interactions will become slightly lesser. There are some practical gases. If I plot their curve, PV curve, like this at different temperatures, this is how they will behave. But for an ideal gas, it should almost be constant like this. Okay, that is PV by T. This is PV by T. So it should be a constant. PV by T should be a constant for an ideal gas. This is how ideal gas would behave. For that you require high temperature and low pressure. These gases practically they tend to deviate away from the ideal gas behavior. So for the ideal gas behavior you require high temperature and low pressure. Then number of moles of the gas can be defined. So for an ideal gas always PV by T should be a constant for ideal gas. Practically some other gases would behave differently. But when you maintain high temperature and low pressure, what can happen is they can have a straight line behavior. They can be as close to a ideal gas behavior. If not the perfect ideal gas behavior, they can be as close to a ideal gas behavior. That is a meaning. Okay. So number of moles, as you have discussed in chemistry, can be N is equal to mass of the sample divided by its molar mass. Correct? Mass of the sample by its molar mass. Also by Avogadro's hypothesis, number of moles N will be number of atoms or number of molecules into Avogadro number of atoms or molecules. So these are some of the hypotheses of Avogadro's hypothesis. You can get number of moles using this. Then what we have to see here is what is the pressure of an ideal gas. Pressure of a gas on a container. This used to be the important derivation, pressure of an ideal gas. Okay. So you compare a three-dimensional structure, cube, so in this only we can think of x, y and z axis. This is, if I take y axis, x, y plane, then obviously this one will become x axis. Okay. Then what about z axis here? This one obviously will become z axis. This one obviously will become y axis on the common track. Then let me know this. Okay. If there is a molecule moving with velocity v like this, moving with velocity v. So this is of side L, okay? Each side of this cube is L, and it goes and hits the container. Okay? It goes and hits the container. Okay? Is that clear? So initial momentum of the gas along y-axis, what happens? It goes and hits the wall. Starting from origin along the y-axis. If it goes and hits this wall, then it again comes back. So initial momentum along x-axis. Consider a gas molecule hitting the wall of the container. Then its initial momentum along x-axis is mvx. final momentum will be minus mvx because it reflects back. No, final momentum is minus mvx. So momentum transferred, change in momentum is how much? Change in momentum 2mvx along x-axis only. All these things are along x-axis. Along x-axis only. Getting it? Okay. This might be moving. See, it is having velocities vx, vy and vz components also. So as it hits the wall, then it gets reflected. So its final momentum will be mvx along x-axis. Okay. Anyway, this formula is more important now, but try to learn the derivation. Okay. So momentum transferred is how much? Change in momentum is momentum transferred. That is 2 mvx. That is 2 mvx. Next you write, in a small time interval, dt, a molecule with x component of velocity, Vx will hit one phase okay, will hit one phase. That means all the molecules within the volume of this, see, if this molecule hits, if this is the area of that phase, if this is the surface area of the phase, then in a small time interval dt, a molecule with the x component of velocity vx will hit one phase. The volume of that phase will be how much? Volume of the phase, that is distance traveled by one molecule. Distance traveled by a molecule is Vx dt. Then that implies, okay, so distance traveled by the molecule is Vx into dt, because it starts from here. Say this is the origin of the Laplace, or see, this is the origin. If I take a molecule, will start from here to hit the face. Okay. Suppose origin is taken from one end, it goes and hits the other face. Okay. It goes and hits the other face. Then the distance traveled by one molecule is Vx into dt. Then how many molecules in a small time dt can hit that space? That is important. Means number of molecules, okay, so as given in your notes, see there, that means all the molecules within the volume Vx dt can hit the wall in time dt, but on an average half of these molecules are moving towards the wall and the others are coming out. So in this volume, if I consider, ನೋಡಿ, ಇದೊಂದು ಕ್ಯೂಬ್ ಈ ತರ ಡ್ರಾ ಮಾಡಿದ್ರೆ ನಾನು, okay, if I draw a cube like this now, where this becomes the origin, where where this point becomes the origin. 1 minute, same as the previous one. Okay, suppose if you think of this, one molecule travels and hits this surface, okay? It starts from origin, in a time dt, it hits this wall. So what is the volume enclosed then? A into Vx dt. So that means, that implies all the molecules in the volume A Vx dt can hit the wall, can hit the face of a cube, correct? That is a number of molecules contained. Hope you understand. That is a number of molecules contained. Okay? But thing is, at a given time, half of the molecules are on the way towards the wall, half of the molecules will be, after hitting the wall, they would be on their way back. That is what is given. So, on an average, gases are constantly moving. No, that is why you cannot take the whole number of molecules hitting the wall all at once. Only half of them can hit, the rest half are maybe getting reflected. Partially some of the molecules are going towards the wall, some of them are coming out. So, number of molecules hitting the face of a cube, in time dt is equal to AVx dt, volume, half n, small n, where small n is number density, that is total number of molecules per unit volume, where small n is number density. Okay, so this is number of molecules per unit volume, unit volume. Momentum transferred to the wall. Momentum transferred to the wall is how much? Number of molecules Na Vx dt, and each molecule transfers the momentum 2 mvx. So what happens now? 2 mvx. So momentum transferred along x-axis is dpx by dt, in time dt, of course, in time dt, that is dpx by dt, it will be n m a vx square. ಇದು ಸಹ dt ಆಗ್ತದಲ್ಲ, dx by dt ಆಗುತ್ತೆ, that is dx nma v square it will become, correct? That is number of transferred in time dt. So dt cancels out there. ಇಲ್ಲಿ ಒಂದು dt ಇರುತ್ತಲ್ಲ, ಇದು dt, vx dt, right? So dt cancels on the other side. Then that is nothing but force, which is nothing but dpx is fx, that is fx. Then what is the pressure? Pressure is F by area, that is equal to N m Vx square. Pressure exerted on the wall should be pressure exerted by the molecules is Nm Vx square. Okay. So if this is a force, this is a pressure exerted in x direction. Idu bari x direction alli Vx square. I hope I repeat it again. It is little difficult, I understand. Okay, normally students find it little difficult. ಸರಿ ಕೇಳಿ, ಒಂದು ಮಾಲಿಕ್ಯೂಲ್ ಇಲ್ಲಿಂದ ಹೋಗ್ತಾ ಇದ್ರೆ, origin ಇದು ಓದ್ತ ಬೇಡ, ಇಲ್ಲಿಂದ ಹೋಗ್ತಾ ಇದ್ರೆ, it hits this wall. Momentum transferred is mvx. After reflection, the total momentum transferred is 2 mvx ಆಯ್ತು. In a small time interval dt, there are ಒಂದಿಷ್ಟು ಡಿಸ್ಟೆನ್ಸ್ ಹೋಗ್ತದೆ ಅಂತ ತಿಳ್ಕೊಂಡ್ರೆ, ಇಷ್ಟು ವಾಲ್ಯೂಮ್ ಅಲ್ಲಿ, ಒಂದು ಇಲ್ಲಿಂದ ಅರ್ಧದಷ್ಟು ವಾಲ್ಯೂಮ್ ಅಲ್ಲಿ, there are some molecules which are half of them are on the way through of hitting the wall, half of them are on the way back of hitting the wall. Correct? Because you cannot have these gases at rest all the time. Okay? So ಏನಾಗ್ತದೆ, half of them move towards the wall, half of them move away from the wall. Is that clear? Okay, so the distance traveled by a molecule is Vh dt before hitting the wall. All the molecules in the volume is area of the face into distance traveled by the molecule. Hit the face of the cube in time dt, that is a Vh dt. Number of molecules hitting the face in time dt is half of this, where small n is number density of molecules, where small n is number density of molecules, that is number of molecules per unit length, number of molecules per unit length. Okay, where I have written it. Momentum transferred is by a single molecule 2 mvx. Number of molecules hitting the wall in small time dt is this. Then that is nothing but force exerted. Then pressure exerted we are calculating. Since the number of molecules are well distributed, I hope I have taken this down. Since number of molecules see V square is given by Vx square plus Vy square plus Vz square. No. Since I take the velocity in every direction is magnitude of the velocity in every direction to be same, then it will be 3 Vx square. Since magnitude of the velocity of these gas molecules which are in random motion will be same in all three directions, then Vx square can be substituted by V square by 3. That implies pressure in every direction becomes N V square by 3. So the pressure exerted by the gas is Mn V square. 1 by 3 Mn V square. So you are averaging the speed. So the velocity of the molecules or the gas molecules in the x direction will be only 1/3 component. You are uniforming it. 1/3 of the total velocity which are substituted. So the total pressure exerted is in a one particular direction is 1/3 Mn V square. Mn V square, where M is mass of the gas molecule, single molecule. N is number of gas molecules per unit volume into V square. Is that clear? This is The important 5-mark derivation. Important 5-mark derivation. So that is about the main derivation. See, as you know very famously, the assumptions of kinetic theory, a given amount of gas is a collection of large number of molecules. All the molecules are in random motion. The average distance between the molecules is 10 times or more than the size of the molecule. Gas molecules do not exert force of attraction or repulsion on any other except during collision. So for that you require, I told you, no, practically the gases show their own behavior. They tend to move away from ideal gas behavior. Okay. Gases show the behavior which is always deviating from ideal gas. Only at high temperature and low pressure they tend to produce a behavior which will be closer to the ideal gas. When they show behavior closer to the ideal gas, there will be very weak interaction between the molecules. Ideally, a gas molecule should not have any interaction with the neighboring molecule. Is that clear? Okay, neighboring molecule. That is important. The gas molecules move in straight line and obey Newton's first law of motion. Gas molecules change their velocities when they collide with each other and walls of the container. That is why we have seen what is the pressure exerted. And these are elastic collisions are instantaneous. Probably these things we have studied in chemistry also. Okay, so this is a pressure exerted by gas. So you mainly remember this formula. Okay. If for preparatory exam at all, if there is opportunity to write preparatory exam, probably learn this for 5 marks. Okay. Otherwise, you remember the formula for competitive exams, where Vx is made V by 3. Okay? V by 3. Next, we shall go to kinetic interpretation and temperature. Kinetic interpretation and temperature. Kinetic interpretation and temperature. So we have just now we have seen P is equal to 1 by 3 mn V square, correct? Mn V square. Multiply both sides by volume. This will be nv V square. This is volume. nv square. Okay. Mn V square, which can be further written multiplying by 2 and dividing by 2 to RHS. PV is equal to 2 by 3. This is total M into total number of molecules into velocity, and half is there. Since I multiplied by 2, I have also divided by 2. Then it will be 2 by 3 n half m V square. Half m V square. This is PV, where capital N, small n is number of molecules per unit volume. So capital N can be small n into V. Now this is kinetic energy, right? This is kinetic energy. So since we know PV is equal to RT, substitute RT here. RT, since PV is RT, since PV is equal to RT, it will be 2 by 3 N, and this is kinetic energy of the molecules. N, that is total kinetic energy of molecules, or 3RT by 2N is the kinetic energy. So kinetic energy can be written as, see, this R by N is regarded as Boltzmann constant. Now, this can be written as 3 by 2 kBT is the kinetic energy of the molecules, where Kb is called Boltzmann constant given by the equation R by N. That implies the ideal gas constant is number of molecules into Boltzmann constant. So what we get is kinetic energy of the gas molecules is directly proportional to temperature. This is what the proof is. Is that clear? Any doubts? Please write it down. So, kinetic energy of any gas molecule increases with the increase in temperature. That is why kinetic interpretation and temperature. Kinetic energy is directly proportional to temperature of the gas molecules. Okay, let us continue now. Okay, next we'll go to degrees of freedom. What do you mean by degrees of freedom? Before that, there is an equipartition of energy. So, consider kinetic energy. I will write it as, consider kinetic energy to be 3 by 2 kBT, right? kBT. It is a total kinetic energy. So this can be written as, kinetic energy can be written as Ex plus Ey plus Ez in all three directions. So, in one dimension, when they move along a straight line, energy along x-axis is half kBT, which will be the energy along y-axis, as well as it will be the energy along z-axis. This is called equipartition of energy. Is called equipartition of energy. It is called equipartition of energy. That means energy along x-axis, y-axis and z-axis for a gas molecule is equally distributed. Okay, energy along x, y and z-axis is equally distributed for a gas molecule. Equal parts, equipartition. Okay, that is from this expression. Idan neevu half kpt bardre and ultimately you are end up getting 3 by 2 kpt, which is a total kinetic energy of the molecule. Hope it is clear. Okay, that is called equipartition of energy. Okay, next is degrees of freedom. Degrees of freedom. See, if I am in a translational motion, I can have the movement in x, y and z axis, no, without any problem. That is my degree of freedom. If somebody wants to locate where I am, he should locate my x coordinate, y coordinate and z coordinate with respect to him. So I am free to move in x, y and z coordinates. I am free to move in x, y and z coordinates. Or if somebody has to locate me, he should know which coordinate, at which position I am and which are the coordinates of that position, x, y and z coordinates. That is called degrees of freedom. That is the directions in which the molecule is free to move, or the coordinates which will help determining the location of the molecule. That is called degrees of freedom. So, degrees of freedom are the number of coordinates, as I told you, coordinates required to specify the configuration of gas molecules. Configuration, position, like that. Configuration of gas molecules. Okay. So, the formula for degrees of freedom, formula is, see, some in your note it is given as n, some write it f also, it is fine. N ante takoduva. Okay. So formula is degrees of freedom is equal to 3x minus L, where n is degrees of freedom, x is number of atoms in a molecule, L is number of independent relations. So, ಈಗ monoatomic molecule. Monoatomic molecule. Monoatomic ಅಂದ್ರೆ single atom. What is the number of molecules? Number of atoms in a molecule? 1. Does it have any independent relation with other molecule? No. So its degrees of freedom is 3. For a monoatomic molecule, its degree of freedom is 3. And Bariri, all the degrees of freedom are due to translatory motion. Obviously, it is free to move, so its xy coordinates will determine its degrees of freedom. Then, what is the total energy of a monoatomic molecule? Energy of a monoatomic molecule. Energy of the monoatomic molecule. ಏನಾಗುತ್ತೆ ಅಂದ್ರೆ ಮಕ್ಕಳೇ, energy in one direction E is equal to half kBT. No, total energy will be Ne. Energy of the monoatomic molecule will be Ne. N is how much? 3. N is how much? 3. It is given in the next page, as you can see, if you want to refer the notes. Otherwise, concentrate here. 3 is the degrees of freedom. In one position, in one direction, it has a degree of freedom half kBT. So the total energy possessed by the molecule is 3/2 kBT. 3/2 kBT. This is a formula to calculate degrees of freedom. Is that clear? Okay, clear? Next, for a diatomic molecule. ಈ ತರ ಇರುತ್ತೆ, obviously connected. So N is equal to 3. How many molecules are there? 2. Correct. 2 molecules are there. Independent relation between them, number of independent relation between them is 1 because they are connected. No, so each atom is connected to other, so there is one independent relation, so that is 5. There are 5 degrees of freedom, that is 3 translational. It can move in all 3 axes, and 2 rotational degrees of freedom. 2 rotational degrees of freedom for a diatomic molecule. 3 translational means each atom or this molecule can be specified by its x, y and z coordinates due to its translatory motion. Also, since there is, see, if I think of this one end of the paper as one molecule and another end as another atom, what happens? It can rotate like this, but they are having that connection. So they have an independent relation. That is why either they can rotate in this way, x-z plane, or they can rotate in rather y-z plane they can rotate, or in x-y plane they can rotate. So there are 2 rotational degrees of freedom. Then for a triatomic molecule, triatomic molecule, see, this is how they are. So number of molecules is 3 and independent relations are 2. Independent relations, this is one independent relation, 2 and another, totally 3, not 2, 3. So in this case it is 6. In this case 6. That is 3 translational and 3 rotational degrees of freedom. What about the total energy? I have written energy of the monoatomic molecule. So what about the energy of the triatomic molecule? Triatomic molecule is obviously energy will be 6 into half kBT will be the total energy. For this diatomic molecule, the total energy will be 5 into half kBT. 5 into half kBT. It depends on the degrees of freedom. So it has got 3 translational degrees of freedom, for which we have seen in every direction the energy will be half kBT by law of equipartition of energy we have seen. In addition to translational, here in monoatomic we have seen only translational motion degrees of freedom it has. But when connected, also the rotational, because it is confined to, this atom is confined to this particular axis and this atom is confined to is the connected axis. Hence the rotation tries to take place. That is why diatomic molecules, in addition to the translational degrees of freedom, also it can rotate about the independent relation axis. They have a relation, these two atoms, by their own attraction. So it gives away 2 rotational degrees of freedom also. Here you have 3 degrees rotational degrees of freedom, 3 translational, total it is 6. Okay, this is how degrees of freedom are calculated. It is the number of coordinates available to specify the configuration or location of a molecule. That is called degrees of freedom. Okay, next we will go to specific heat capacity. Next we shall move on to specific heat capacity. in terms of a universal gas constant. Okay, so specific heat capacity for a molecule having n degrees of freedom. A molecule having n degrees of freedom. N degrees of freedom its total energy can be half kBT into N, correct? Half kBT into N. Half kBT into N. Then this is equation 1. That is a total energy it possesses. Okay. Next, for a solid, vibrating about its mean position. For a solid, it vibrates about its mean position. No. This is N by 2 kBT. So total energy will be N by 2 kBT. This is for a molecule having n degree of freedom. Now you consider a solid of n molecules vibrating about its mean position, because there will be interaction, no, about its mean position, vibrating about its mean position, then it will have 2 degrees of freedom. One is due to its vibration, another is due to its kinetic energy. One is due to its vibration, another is with the interaction. So it will have 2 degrees of freedom. So this is its total energy. For n molecules, it will become n kBT. N molecules, it will become n kBT in 3 dimensions. If it vibrates 3-dimensionally, in 3 dimensions, the energy will be 3 kBT into N, which I can write it as 3 RT. So the total energy is 3 RT. Since KB is R by N. So N KB is R. Okay. N and KB is R. Then dE by dt, I can also write it. It is with respect to temperature. I can write it as energy. As it absorbs energy, it tends to vibrate. So the specific heat, internal energy. So as it absorbs the energy from within, this will act as an internal energy. So when I differentiate with respect to the temperature, this is the specific heat. So This is the specific heat. Then, so for a solid you have considered, then pressure so this is nothing but specific heat capacity as the pressure does not change. Okay, so as pressure does not change the internal energy, as pressure does not change internal energy of the molecules, as the pressure does not change the internal energy of the molecules, there won't be change in volume, no. So work done will be zero only. Work done will be zero. Okay, so whatever the change in internal energy, it is due to the heat absorbed. It is due to the heat absorbed. So the specific heat capacity dQ by dt should be equal to du by dt. So specific heat capacity of a solid is 3R. Specific heat capacity of a solid is 3R in total at constant pressure. Okay, at constant pressure. So this is a specific heat capacity of a solid. Next, they have given, derive the expression for specific heat of water in terms of universal gas constant. Specific heat capacity, specific heat of water. So you remember for solids, the specific heat capacity is 3R. Okay, same way, you just see this is a general expression of energy. This can be written for n such molecules, all those things. So the specific heat capacity for a is that clear? Okay, now specific heat of water, specific heat capacity of water. So just think of assuming water as a solid triatomic molecule, it will have, assuming water as a triatomic molecule, because it is H2O, right? Assuming water as a triatomic solid molecule, as a solid triatomic molecule, because of its configuration H2O, ಎಷ್ಟಾಗುತ್ತೆ number of degrees of freedom 6 ಆಗುತ್ತೆ ಅಲ್ಲಿ. So contains 3 atom. Now average energy, solid triatomic molecules, so its average energy will be 3RT. That is 1 mole of the solid consisting of n atomic molecules. Average internal energy will be 3RT because it will be confined in all 3 directions. Okay. Then it has got, that is it has got 3 by 2 RT, that is the average energy. of the molecule. So average energy in all directions. Average energy in all three directions is 3 by 2 RT. You write it properly. It is 3 by 2 RT, similar to what we have done, 3 by 2 kBT. There are n such molecules. For n molecules contained, Sariya, R andre no, n kb, that is R. Okay. Next, this is average energy per unit per n molecules ಆಗುತ್ತೆ. Next, in one direction, no, total energy will be how many degrees of freedom it has got? 6 into 3 by 2 RT it will be. 3 by 2 RT it will be. So it will be 9 RT. So the total energy is 9 RT, which will be written as U. Then du by dt is equal to d by dt of 9 RT. So that is equal to 9R, which is a specific heat capacity of water. That is specific heat capacity of water is 9R. See, there is a derivation for mean free path, but as far as for exam, that is not required. That is why not going to derive that one. Anyway, this will be done again in CT synopsis. So you just take the definition of what is mean free path. That is more important. Mean free path is the average distance covered by the molecule between two successive collisions. It is an average. So the mean free path lambda is given by 1 by n pi d square into root 2, where n is number of molecules per unit volume, number of molecules per unit volume. D is diameter of the molecule. Clear? Okay. So D is diameter of the molecule. Pi is obviously a constant. So lambda is called mean free path. So that is, see, there will be lot of molecules together, no? Suppose if this molecule has to move without collision, there is a very less chance that it will move without collision. However, if it starts to move without any collision, there will be random movement of other molecules also. They are approaching or going away from this molecule. The distance, suppose after this collision here, it moves in this direction, then it collides. Then this is the average distance. You cannot always have the exact distance in place. It will only be the average distance in place. Is that clear? Okay, that will always be the average distance in place. Try to remember this formula. Derivation is required, but it is blown up. Okay, Derivation nobody will ask now. Try to remember the formula for mean free path. That is the free path, average free path, which is free of collisions. That's all. Otherwise, whenever the atom moves within the molecular system, what happens? It tends to undergo, the molecule tends to undergo collision with the neighboring molecule. Is that clear? That is why such a path is called mean free path. Such a path we call it as mean free path. Now, just for your competitive exam sake, try to remember CV is du by dt, that is equal to 3R, no? That is equal to 3R for a monoatomic molecule. 3 degrees of freedom, no? Monoatomic molecule. For monoatomic molecule, CV will be 3 by 2 R it will be, because energy will be transmitted in all directions. Okay? Because total energy U was 3 by 2 RT, right? So now it is CV is du by dt, that is 3 by 2 R. CP is CV plus R, correct? Which is 3 by 2 R plus R, so it is 5 by 2 R. Gamma value, the gamma value is ratio of Cp by Cv. Gamma value is ratio of Cp by Cv, which is 5 by 2R divided by 3 by 2R, which is 5 by 3. This is for a monoatomic molecule. Next, for diatomic molecule, it has got 5 degrees of freedom. So average energy, diatomic molecule, the average energy is 5 by 2 RT, implies CV will be du by dt, which is 5 by 2 R. CP then becomes 7 by 2 R. Formula ಇಲ್ಲಿ ಕೊಟ್ಟಿದ್ದೇನಲ್ಲ ನಾನು, ಅದೇ ತರ ಮಾಡ್ಕೊಂಡ್ರೆ ಆಯ್ತು. Then gamma value for diatomic molecule is 7 by 2 R divided by 5 by 2 R, which is 7 by 5 R. Okay, 7 by 5, that's all number it is. 7 by 5. Then for triatomic molecule, obviously degrees of freedom, n is equal to how much, you tell me? Degrees of freedom is equal to degrees of freedom is equal to 6 for a non-linear molecule, for a non-linear triatomic molecule. Then it is, its gamma value will be how much? It is Cp by Cv. Cv is U is equal to 6.5 kBt. So Cv is 3R. Then Cp should be 4R. So it should be 4 by 3. Gamma value is 4 by 3 for a triatomic non-linear molecule. Okay, non-linear molecule. So you mainly try to remember gamma values from this, and also you try to remember ನೋಡಿ ಯಾವ್ದೆಲ್ಲ ನೆನ್ಪಿಡ್ಬೇಕು, gamma values for diatomic, triatomic and monoatomic. Pressure equal to 1 by 3 mn v square, that formula, gamma values. Then specific heat of water is 9R, just now we have proved, 9R we have proved. Then kinetic energy is always proportional to temperature, because kinetic energy is 3 by 2 kVt for any one molecule. So that will conclude the session for today. No numericals from this chapter. Okay. So in next class we will start waves. Okay. Thank you.